Hello everyone, this is Meher Baba. I'm currently doing my BTech second year in School of Computer Science Engineering at VIT Chennai. Today I'm gonna discuss you about the applications of context-free grammar in speech recognition. What is a context-free grammar? Context-free grammar is a set of rules or predictions for a given language. It consists of set of predictions or rules that define how to generate valid string of the given languages. Notations. Generally, a context-free grammar is denoted by capital G, and it is a four-tuple which consists of V, sigma, P, S. V is a set of non-terminals, and sigma is a set of terminals. P is a set of predictions or rules. S is the starting symbol of it. And generally, a context-free grammar G is denoted by A tends to alpha, where A belongs to V and alpha belongs to V union sigma whole star. A CFG consists of two sides, LHS and RHS. It has two types of symbols, variables and terminals, in which left-hand side always contains non-terminals and the right-hand side consists of a string of 0 or more variables and terminals. Capabilities of CFG. There are various capabilities in which the important one is it describes most of the programming languages and it is properly designed, then an efficient parser can be constructed automatically. And a context-free grammar is capable of describing nested structures like balanced parentheses and if and then loops. The Chomsky hierarchy. Generally, in this diagram, we're gonna see the regular language inside a context-free grammar and the context-free grammar whole inside a context-sensitive grammar, and it is inside the recursively enumerable, in which generally regular languages is a subset of these context-free grammars, in which all the regular grammars are said to be context-free grammars and all the context-free grammars are said to be context-sensitive grammars, which is denoted as context-free grammar is subset of context-sensitive grammars. Parsing. Parsing is generally a process of making parse trees or tree structure from a given string and grammar, and it is completely analogous. Ambiguous grammar. When a grammar is said to be ambiguous if and only if it is having two leftmost derivatives or two rightmost derivatives, which is mentioned in this first line. L of g is greater than 1, which means it must have two or more leftmost derivatives, and here greater than 1 parse trees or rightmost derivatives, where it is having two or more rightmost derivatives. In the second line, it is telling that when a context-free language is having a context-free grammar having two or more left derivatives, but it is not valid in all cases. In some cases, it may not be ambiguous. Some examples of ambiguous grammar. We can see first the set of predictions. The first prediction is E tends to I, and where I is the set of 0 to 9 numericals and plus into and open and closed parentheses. Second prediction is E tends to E plus E. Third prediction is E tends to E into E. Fourth prediction is E tends to parenthesis E. Now see one of the leftmost derivative of it having example 3 into 2 plus 5. First taking E equal to E into E and now making this E into I from the first production set, and next I into 3 from the first production set, and next E tends to E plus E. Now this E tends to I and the second E tends to E only, and again I tends to 2, E tends to E same as it is. 3 into 2 plus E tends to I, and finally I tends to 5. We made 3 into 2 plus 5 by using E into E as first. See second leftmost derivative. The first thing is E tends to E plus E. and again they are making E and second E as it is. Now making one of the E as I in next step. Now I as 3 in next step. Now again E into I and again second E as it is. And again making I into 2 and again next E into I and again it is making into 5. So in these two leftmost derivatives, what we have identified is first leftmost derivative we got from E tends to E into E, and second leftmost derivative we got from E plus E. So these are two leftmost derivatives which we got from the same prediction set for the example 3 into 2 plus 5. So having two different leftmost derivatives, we can draw two different leftmost trees for this, which are parse trees. The first parse tree one is E tends to E into E, again E tends to E plus E, and again E tends to I, E tends to I, E tends to I. And second parse tree is E tends to E plus E, and again first E tends to E into E. Therefore, we are getting two different parse trees which are from two different leftmost derivatives. Hence, we can tell that this grammar is said to be ambiguous. This is the first parse tree. This is the second parse tree. Now let's see applications of context-free grammar. The first one is CFG phrasing for high-speed networking applications. CFG is used for high-speeding network applications, and it is also used for data processing, and it is used in natural processing of languages, and again it is used in human activities recognition such as voice recognition, speech recognition, etc. And the final one, every context-free grammar can be converted into parser, which is a compiler, and it identifies the structure of the program and converts it into tree. Coming to speech recognition. What is a speech recognition? Its task is to convert the speech into sequence of words by a computer program. Example, Google Assistant. It tries to identify and a sequence of words from speech signal, and this is typically done by limiting valid recognition hypothesis to phrases that are found in context-free grammar. A method of managing grammars used in speech recognition system comprising. The first one is loading the grammar into context-free grammar engine, and the second one implementing an engine independent SR interface between the CFG engine and a speech recognition engine. Communicating the words in the first grammar to SR engine through a SR interface is the third one. Coming to fourth one, notifying the SR engine through SR interface of rules in the first grammar. Fifth one, representing the rules in the first grammar to SR engine through the SR interface. Sixth one, receiving rules queries from SR engine through SR interface. Seventh one, representing the first and additional grammars to SR engine through the SR interface as a single grammar. Eighth one, communicating the words in the additional grammars to SR engine through SR interface. Ninth, notifying the SR engine through SR interface of the rules in the additional grammars. And finally, 10th one, representing the rules in additional grammars to the SR engine through SR interface. See the figure 6 here. It is a flowchart diagram illustrating how a speech recognition engine builds an internal representation of a loaded grammar. And see its flow. And the figure 7 is a flow diagram illustrating how a grammar content is changed in according with one embodied of present invention. This is the complete speech recognition process, and how the user is giving the words, and how the voice engine is recognizing, how it is decoding, and how it is transforming into a text. The current innovation comprises a context-free grammar engine that interacts with a speech recognition engine through an accessible interface. In one example, embodiment, the CFG engine manages the loading and unloading of grammars and preserves the intent activation state of loaded grammars. Moreover, the CFG engine consolidates all loaded grammars and their activation states into a single grammar, which is presented by speech recognition engine. Now coming to background of the invention. A speech recognition system involves a computer attempting to identify a series of words from a spoken signal. Here, this is achieved by restricting the recognized phrases to the present in a context-free grammar. Previously, the applications utilizing these sequence recognition engines would directly communicate with the engines, but here it won't take place. Now coming to conclusion. The current invention reduces the workload for both speech recognition engine and the context-free grammar handles various tasks such as grammar loading, activation, deactivation, invalidation, as well as addition, deletion of words, and rules of dynamic grammars, etc. Here it loads multiple grammars and generates a comprehensive result from it. The SR engine preserves the information from the CFG engine as well as single grammar with rules and words are added, deleted, activated, deactivated at any intervals. Consequently, the SR engine can focus on speech recognition without being concerned with various tasks performing in the CFG engine. I hope my video is informative on this context-free grammar and its application in speech recognition. Thank you.